sorry, today I had a skill issue.
Yeah. Okay, a letter, sure. A letter
Why,
still doesn't have
why didn't you buy a bigger super coat? I still don't get it.
because I bought a used one. I just didn't go to the period.
There's, I mean, you could.
No, because a new one with import tax would be like $600.
Yeah, no, that I know, but like, remarkable isn't like decent enough.
It's okay. I wanted the super better. I only need this for writing, and I only need a tablet for writing. Right? Yes.
He passed
It's the
linear algebra last year in the other program he was doing. That's why he wasn't here.
No,
no. He was talking about
Hair.
no hair.
It's the barber that's under the.
How much did he charge you?
Yeah.
80 shek.
Yeah, 80 shekels and like 15 minutes.
I mean, that's not that bad. Like,
Okay, guys. So here we go again. Lucky you, 5 hours with me on Tuesday. So now we're back to calculus. And the original discussion was about the same. We talked about the number systems, but in calculus we talked about calculus problems like square root of 2 and needing to exist. Where is it? Here. We expect there to be a square root of 2, but there was none. So we have the real numbers. And in algebra, we spoke about algebraic problems and algebraic constructions. And that's the introduction about numbers for both courses. And now we're moving on. And the last thing we discussed, it was the last minute of the class, or even a bit after. And I wanted to show you that even the operations, like the power operation, requires limits in order to define. 3 to the power of square root of 2 is actually the limit of the sequence of approximations to the square root of 2. We didn't define limit yet, and we won't define the power operation in this course. But again, this was an introduction to show how much limits are in the heart of everything in calculus. And now we wish to move for the first real subject in calculus, which are boundaries or bounds, I don't know, chasamim in Hebrew. And sorry, I will start with the example I like from the Torah. I don't remember the numbers because I didn't prepare it ahead, but you will get the idea. Abraham speaks to God, and God tells him he's about to annihilate Sodom and Gomorrah. And Abraham tells him that that's not okay to annihilate the whole city. What if there are good people there? And he tells him, what if there are 50 good people in Sodom and Gomorrah? And God tells him, then I will spare the city. And Abraham is a bit of a nudnik, and he said, what about 40? And he said, I will spare the city. And he goes down, and I think he stops at 10.
Stops at 2.
He doesn't stop at 2. He doesn't stop at 2. I think he stops at 10. And God tells him, enough is enough, leave me alone. And then we find out there was one saint, one good person in Sodom and Gomorrah. So he said, okay, take him out. I'm not sparing the city. And the thing is that what did Abraham wish to learn? Why did he ask him 15 and 40 and 30, 20, 15, 10? Why did he ask? What did he try to find? But all of them are boundaries, but he wanted to find
The limit.
Well, the limits will be later, but he wanted to find the
The minimum.
trying to say in Hebrew I will say chasam aduk, but
The
the
precise
best
lower bound.
the best bound. Okay, will because there will be exact definitions for what I'm talking about, but now I want to do it in a more simpler terms. Right. So we wanted to find the best bound, which is exactly the tipping point from sparing the city and not sparing the city, and it was not given in the Torah. He skipped from 10 to 1, and he
No.
didn't go all the way to 2.
Are you sure?
Yeah. I made a, yeah. Look for it afterward, but I remember because it's always my point that why did the Torah did stop at a higher number, and I think it was ordered to say there is no exactly hard tipping point. I may have spared the city for 3 and may not. It depends on such and such, but that's my interpretation. That's not math. But the thing is, we wish to find the finer bound, the best bound, and as such, we will need in mathematics as well. And Thomas said its limits, and not exactly, but the boundary, the supremum and infimum, the best bounds are the introduction to limits. Limits are a bit more complex, but this is the first notion, which is kind of like limits. Okay, so that's the story. And now I wish to give you a mathematical example. So first of all, you should know notation. If I write A to B, I mean all the real numbers that are from A to B, not less than A, not more than B. If I use the round bracket, that means not including. So these are all the real numbers which are greater than A and lesser or equal to B. Okay, this notation is fine. Where those brackets are round, it's a bit confusing because it looks like a segment and it also looks like a point in the plane, but that's life. Mathematicians use the same notation for 2 different things, and you need to understand from the context what do they mean at this certain point. Okay, so now and again, we're in the introduction. I will give the exact mathematical definitions a bit later. Now I'm just asking questions. So example, if I look at the set 1, 2, 3, 4, 5, what would you say is the lowest? What would you say are the edges of the set? It's not a mathematical definition. The mathematical definitions will be supremum and infimum, but for argument's sake, what would you say are the edges of the set of the numbers 1, 2, 3, 4, 5?
Yeah, 1 and 5.
1 and 5. Yeah, it's not a trick question. 1 and 5. Now, why? Why would you say 5 is the top edge of this set? It's the biggest number, right? It's easy since 1 is the lowest.
You're not ready.
Lowest number.
You're not typing.
I am typing, you're not
It's catching up.
seeing,
It's
it's
catching up.
something else. Yeah, okay, but thank you.
Technically not though.
No, that's not my computer.
No,
No, no.
I'm saying
Ah,
it
you're
doesn't-
talking about mathematics, but wait a second because the Zoom connection was lost. And it's back. Okay. So yeah, so 1 is the lowest number in this set, and 5 is the biggest. So what did you mean by technically not?
well, because that's only if you're doing this as like a partial order set from where it's like the order is bigger than.
Yeah,
If there's a different order to
No,
not with the discrete mathematics.
Yeah, don't talk, he's talking about the real.
No,
numbers.
but you're right.
He's talking about if you're actually.
You are right with this Itchakmut. In calculus, we only use the real numbers and the order, the regular partial order. Yeah.
The trivial
And
order.
yeah, you probably define supermoon bounds on discrete mathematics in a much more complicated scenery. It's the very same definition, but it's much simpler here. And yeah, I did ignore the fact that most of you have heard these definitions in another scenery before, but yeah, it's just the regular order and the real numbers. Okay, maybe the rational numbers as well. We'll speak about them a bit. Okay, so this is the lowest number and 5 is the biggest. Now look at the following set, and let's call it A, of all the 1 over n, the inverse of the natural numbers, such that n is a natural number. That means 1/2, 1/3, and so forth. What are the so-called edges of the set A?
1 and 0.
So you would say 1 and 0, right? 0 and 1. 1 being the biggest, which will be called maximum, right? But why 0? Why is 0 an edge of this set? It's not there. It's not the lowest number.
Because the set is infinite and there for every element there's an element that is smaller, then 0 must be the edge.
You said a theorem which has nothing to do with 0 and then says 0.
No, I mean if you because there's no minimal number.
Yeah, that's the problem. But why is 0? Why did you choose 0 to be the edge? You are reiterating the problem. There is not minimal number.
I mean, you never said that the edge should be part of the set.
But why do you say 0 is the edge?
Because
These are all circumstantial evidence that you give me, but why 0? Why not pi? And why not -100, right? What is so special about 0? Yes.
Because the set is infinite,
Yes.
and because every number after our current number in the set is smaller.
That's exactly what he said.
No, because but because it's infinite and it tends to a smaller number, 0 must be.
Again, all you are saying a lot of sentences, none of them has anything special to do with 0, and then you say, and that's why it's 0. But why not pi? Why not -100, right? Yes. So that's yeah, I don't like that answer.
let's
But
say
because infinity is not a number and it's not completely false, but it's basically you're using limits of sequences, which is a more complex notion than the edges that I wish to show you. Yes.
The approach 0 but never pass it.
So it's again the same thing. It's going. It's okay. What? Oh no. one thing you said I liked. You say it's approaches zero and not past it. Well, I didn't notice that at first when I
So-
said no, but it also approaches. Okay, I wanted to write it because it is on the way to the right answer. It approaches zero and not past it. It also approaches -1 and not pass it. Agreed?
Because zero is the biggest
Yeah.
number it doesn't pass.
Zero
Small.
is the biggest.
The biggest.
The biggest is
Right, yes, sorry.
the biggest number which it doesn't pass. Again, from discrete mathematics, you should know it because that's the definition. And the infimum is the largest lower bound, right? I will redefine it in this course, but that's the idea, and that's kind of what Abraham was going for. He was going lower and lower and lower and say what is the lowest number which we don't pass, the tipping point. But again, it was stopped beforehand. Okay, so also similarly, the so-called edges of the set from, I don't know, 0 to 1 will be 0 and 1 from and the same because of the same reason. Okay. So again, this was introductory. In just a few minutes, I will give the very exact mathematical definitions, which we will use later. So, definition. Given a subset of the real numbers, we say that, no, sorry, and M, any number, any real number, we say that 1, M is an upper bound of A. In Hebrew, I will write it, like I said, for you to know in the future. Second, okay. Chassam Mil-El. You actually use this in computer science because when you have a complexity of an algorithm, you use upper bound and lower bound. So the lecture quite possibly will say Chassam Mil-El and Chassam Mil-El. So M is an upper bound of A. When will you say a number is an upper bound of a set?
When no element in the set is over that number.
Yeah, when it is larger and equal to every element of the set. If for all A in A, it is true that A is lesser than or equal M. So notice that the upper bound could be a part of the set, but it also might not be. So 50, 40, 30 are upper bounds of the set Abraham was searching. There are many upper bounds, okay? And the special one is the supremum, which is the lower upper bound, and I will say it in a few minutes. And I will define everything from above as from below. M is a lower bound of set A, Hassam Milra, if for all A in A, M is lesser than or equal to A. Agreed? 3. M is called maximum of A if M is an upper bound of A. And what else? When will we say that an element is the maximum of the set?
If it's bigger, I know, it's maximum.
If it's in the set.
In the set,
In the set.
and M is in A, exactly. Okay, so if it's larger than all other elements of A, but it is a part of A, upper bound does not have to be. So for the sake of argument, say that for 2 people, God would not annihilate Sodom and Gomorrah, but for 3 people, he will. So the maximum of number of saints for which God will not annihilate the city is 2, right? And so if it is within the set, and like we've seen before, the edges, so-called edges, supermum, infimum, does not have to be within the set. However, when they are in the set, they are the obvious edges, right? That's well, I'll go to calculus from the high school in a minute for like graphing, but if it reaches its goal, it's an obvious edge. That's the easy case. It's more interesting when it infinitely moves and does not reach its goal. But both of them will be considered so-called edges, infimum, supermum. So M is a maximum if it's an upper bound within the set. M is called minimum of A if M is N, I wrote and is a lower bound of A and M is within the set. And lastly, the last 2, we say stick to the same phrasing. M is supremum of A or sup A if it is the minimum of the lower upper bounds of A. If you have the minimal lower upper bound, the smallest upper bound is like the word supremum. If you come from above and you want to find the edge of the set, so from above is the closer to the set, so it will be the lowest from the numbers above. And M is the infimum of A if it is the maximum of the lower bounds of A. Now, question for a second for whoever took discrete math. Did you learn all these notions in discrete math? I will show you for a second.
Yeah.
Called post-trauma. We see that these are the very same definitions, but just for a general partial order, and we do it for the specific partial order. Look, and there were a couple more. So maximally הגדול ביותר, for all A, חסם מלעיל, for all A, RM, it's basically the same, right? Whoever didn't learn it yet, it doesn't really matter. I'm just saying it's the very same definitions. They also have maximally and minimally, which are relevant when the partial order is not linear. Here, the partial order is linear, so we don't need the other two definitions. So these are the definitions that we are using. For example, first example, we will prove that 0 equals the infimum of the set of the 1 over n when n is natural. Right, we saw this example before. You immediately say that you feel that the edge is 0. Now we have a mathematical definition, and we are able to prove beyond a doubt that 0 is the infimum of that set. So what do we need to do? We need to prove that 0 is a lower bound of the set. And what else do we need to prove in order to say it is the infimum? How many lower bounds does this set have?
Infinite.
Infinite, right? Every negative number is a lower bound, right? So we don't just need to prove that it's a lower bound. What else do we need to prove? No. It's the maximum of the lower bounds. And also that 0 is the maximum of the lower bounds, right? We have many lower bounds on the left. If we think of the axis, many lower bounds, 0 is the maximum between all of them. That's what I need to prove. Agreed? So let's do it. It's 2 steps, 2 different things. First is proving a lower bound. How do I prove a lower bound? Generally, when we wish to prove a mathematical
Hypothesis? No, not really.
Like in logics, how do you, the logical expression, what name did you use?
Argument?
I don't know. Well, I use a statement.
Yes,
When
statement
you-
works.
When you wish to prove a mathematical statement that start with all elements of a set, for all elements of a set, a certain statement hold, you always use in Hebrew the word yehi. In English, you would say, assume A is in A, or letter B, A in A, or something like that. In Hebrew, it's always yehi. And the idea behind it is if I'm given an arbitrary element of the set and am able to prove my statement toward an arbitrary element, that means that I proved it for all elements. In order to prove that 0 is a lower bound, I'm actually saying it's smaller than all elements. So I need to take an arbitrary element and show indeed 0 is smaller than it. Okay, so I will write assume or given in this case. I don't know. In Hebrew, it was there is no argument. I will always say yehi. Yehi echad chelkei n in the set. In English, I think it's
let.
less. Yeah, I said let, assume, given. I think it's less restrictive than in Hebrew, but they're all meaning the same, given an arbitrary one, right? So given, I will write an arbitrary 1 over n in the set. So given any arbitrary element of the set, we need to prove that 0 is less than or equal 1 over n, which is obvious. All natural numbers, they are positive. Well, the inverse is also positive. That is true. We have nothing to prove in this case. In other cases, it might be a hard thing to prove. In this case, it's obvious that 0 is a lower bound. Agreed? Now, given an arbitrary lower bound M of this set, what do we need to prove?
That it's smaller than 0 or is 0.
That M is smaller or equal to 0. That proves that 0 is the largest lower bound, because it is a lower bound and all lower bounds are smaller or equal to it. Agreed? Okay, great. Now, another thing which is a language barrier, in Hebrew, there is a great phrase, naniach beshlila.
Will assume by contradiction.
Yeah, in English, it's much less spoken. You don't use it. You usually say, I don't know, assume otherwise or something like that.
We say assume by contradiction.
Okay, so assume by contradiction, that's A, B, C. Oh, wow, great. So A, B, C, assume by contradiction. In Hebrew, I write nabash, naniach b'shlila, so I like so that's good. ABC, that's all of them. ABC. Okay, I will use it because I use it quite a few number of times. So assume by contradiction that the lower bound M is larger, from 0. What is the contradiction here? Why is there a problem that the lower bound will be lower than 0?
Therefore.
But that's not true. It's on the way of the true answer, but what you say is false. Not every number larger than 0 is a fraction. First of all, there are numbers larger than 1, but not just that. What about 2/3? That's not a fraction of 1 over n. So not exactly, but we'll say the following. Choose n, natural n, such that 1 over n is smaller than m. Why are we able to do this? Indeed, there exists n which is larger than 1 over m. Do you agree about that statement? For any real number, there is a natural number larger than it. Does that make sense? Everywhere on the real axis, there will be any point you will choose, there will be a larger natural number. That's called Archimedes' law. Archimedes' law. And if n is larger than 1 over m, what can you say next? If n is larger than 1 over m, you can
Say that then is one or bigger.
multiply by n and divide by m. I'll do it in 2 steps. So 1 is larger than n over m. Now, sorry. 1 and 1 over n times m. I divided by n. Now multiply by m, which are both positive numbers, right? So m is larger than 1 over m. In the future, it will be considered obvious. I'm within the mathematical expression. And I still am, but whatever. In the future, it will be considered obvious that if I have a positive number, I could choose a natural number such that 1 over n is smaller than it. And that's the fine-tuning of what you said. It doesn't have to be, but there is someone smaller than that. And what is the problem with 1 over n being smaller than m?
Then it means that it's part of the
Not
set.
part of. M was supposed to be a lower bound, meaning smaller than everyone. But 1 over n is within that set, and it's strictly smaller than m. That's the contradiction, which contradict m being a lower bound of the given set. Okay, so that's the proof, the tedious proof of the zero being an infimum of the set. This proof may seem tedious, but most proofs in calculus are as such. So it doesn't contradict that it is tedious, but don't do the mistake, make the mistake of thinking, okay, that's a tedious proof, but the rest will be fun. No, this is the way we prove theorems in calculus, and I started with the easiest ones.
This is not fun. It's not supposed to be fun.
Yeah, you need to suffer. If at any point you're feeling you are understanding something, please raise your hand and I will tend to you. Okay, but yeah, and calculus is kind of I think it's the most tedious one. Well, you did learn discrete mathematics, which was also very tedious, but still calculus. The reason calculus is a bit more tedious is because the concept of a limit of a sequence is more convoluted than anything you've seen in discrete mathematics. The silver lining is that the silver lining is that it is one concept and we use it a lot. So we get used to it. In discrete mathematics, all the time you get new definition, new definition, new definition. So that's a different type of challenge. So the limit of the sequence is more complex than any definition you've seen in discrete mathematics, but it's one definition. We will see it quite early in the course, and then we will regurgitate it over and over. So
Yes, math.
Oh yes, suffering, yes. Okay. So we have first proof of an infimum. Now, another example, which is an interesting one in my opinion. Say M is the maximum of the set A. Prove that M is also the supremum of the set A. This is have something which is philosophically important. What did I tell you before? If I have a maximum, it's the obvious edge. When I'm nearing an invisible edge, I use supremum. But I want the supremum to hold both the hard case, but also the easy cases, right? We said when we have a maximum of a set, the biggest element of a set, it should be obvious that it's the supremum. But it's not obvious from definitions. We need to prove it, because the definition of the supremum is the lowest of the upper bounds, right? So I'm claiming basically, and I will write it, in other words, we claim that the maximum is the lowest of the upper bounds. And it's, I said in other words, but basically these are the same words because that's the definition of supremum, but it's literally other words that are written here, okay? So we need to prove that the maximum of the set is definitely the lowest of the upper bounds. So again, I need to do two things. First, to prove that it's a lower bound, an upper bound, sorry, excuse me. That's true by definition. I will write it. M is an upper bound of the set A by definition, and whoever does not remember, I'll go to the definition. M is called a maximum if it is an upper bound. That's by definition. And also a member of the set. So the fact that M is an upper bound, that's by definition. Now I wish to show that it is the lowest such upper bound. So now, given an upper, and I won't write arbitrary all the time, but I mean arbitrary, given an upper bound K of A, of the set A, what do we need to prove?
Given the upper bound K of A, we want to prove that it's the maximum, or
No, so let me show you on using a drawing. I think it will help, and I didn't do any so far. This is A. Where is the maximum of A in the drawing? At the very edge of the set. Agreed? So it is an upper bound by definition. It is bigger than all the elements are equal. Now, I'm taking an arbitrary upper bound of A, K. Where is it? Where is K in the drawing?
it's supposed to be to the right.
About is here, right? But M supposed to be the lowest of all upper bound. So what do we expect the relation between K and M to be?
K to be bigger than M.
M to be lower or equal to K. Agreed? So that's what we need to prove, and then we prove that it's the lowest upper bound, meaning the supremum. Who here has any idea why is M lesser or equal to K?
we said that, wait, did we say M is the maximum or we said,
M is the maximum.
so, if K equals M, that's the trivial case. If K is less than M, then it's not the maximum
Why?
because it's another element in A which is not bigger than every other element.
If K is lesser than M, it doesn't mean that it's within M, within A.
I mean, it's not, if it's smaller than M and M is the maximum, then it's not an upper bound
Why?
because
You're correct, but why?
because it's not bigger than every bigger or equal than every other element in
From
A,
which element of A is it not bigger?
the maximum.
M itself, exactly. And now when we understand that, the answer is quite easy, but it's hard to get to yourself. Since M is a member of A and K is an upper bound, then M is less than K. And it's funny to see it like that, but that's the very definition. The definition of an upper bound is a number which is larger than everyone in the set. But M is a member of the set. Then Bifrat, specifically, K must be larger than M as well. It's larger than everyone. Okay, so we finished this example. It seems a bit like magic, but that's true. And it's also true in general in discrete mathematics. The maximum is always the supremum, and the proof is the same. Any questions thus far? Okay. So we have the notion of supremum and infimum. Now a bit of a discussion about infimum and supremum and asymptotes from high school. Look, watch. That's linear algebra. Take the function arctan of x. Well, we will learn about this function in the future, but for now I'm just drawing it. That's the inverse function of tangent x. So it has an asymptote in the infinity direction. When x tends to infinity, the arctan function tends to this y value, which is y equals pi over 2. Okay, you don't have to know why does the inverse function of tangents tends to pi over 2, but it is important for me, it is important for you, I think it is important for you to understand the drawing. And what happens here is the function is infinitely increasing and tends to the number pi over 2 as x goes to infinity. So why is that the asymptote, and what does it have to do with the bounds that we learned about? Is pi over 2 the only upper bound in the y-axis of the function? No, there are infinite number of upper bound, but it is the lowest one. Does the function ever reaches pi over 2? No, why not? If it did reach it, because it's increasing, it will pass over it and it won't be a bound anymore. Agreed? So limits are a bit more convoluted. Why? because also if I add to the function 1 over x, not exactly what I wanted. 1 over e of x, no, it's also positive. Oh. Yeah, I think that's fine. So I took this function, the asymptote is still pi over 2. Is it true that half pi is an upper bound of the function? No.
Yes.
Here it's these numbers on the function are bigger than half pi, but still the asymptote is half pi. Why? Because limits are more convoluted and they are not just strictly speaking about bounds, but they are speaking about what happens when x is at a certain area. We will learn about limits later. Now we are in the easy case where bounds are all that we look at. Yes.
I was gonna ask if that graph was on the positive real numbers, then pi over 2 would be the bound.
What do you mean? The other graph or this graph?
Wait, the other graph, last graph. The graph we
Okay,
had.
so I'll go
You
back
said
to
it,
it.
you said it wasn't because there were values that were higher
Yes,
than it, right?
yeah.
But
You're
if
you are
take
correct
off
that
those
if I take
values,
just the
just
positive numbers,
then
it is an upper bound.
Real numbers, you mean like in the
positive real numbers.
Yeah, it said positive number. You're correct. If I look just at the positive numbers, it will be an upper bound. I can show you if you're asking right now even worse examples. Plus hold on to your seats. Wait. I example. Oh, that's great. Okay.
Yes.
Beautiful. So here, the asymptote is still pi over 2, but here it's not a bound at all.
Seems like a code 2 problem.
Why is it always positive? Something is weird about it. Why is it always less than? I wonder. Because of the 1 over e to the x, I think. In any case, it could go over. I think it's a bad example because it's actually always under the bound. Well, let's fix it. Just a second. I think you will do this. No, why not? I know what to do. 5 times. No. Ugh. What am I missing? 10 times. I think it's just okay. Just some matter of numbers, but always from some point on it's closer. Last try. The Zoom collapsed from the horrible experiment I'm conducting. So it could be as such that it's not an upper bound at all, never, right? This function always goes above and beyond to infinity, but it's still the asymptote because it tends to have a pi, okay? But again, that's limits. They are more complex than just bounds. So let's get back to the bounds. Easy example. Okay. So half of pi is the upper bound of the function, negative half of pi is the lower bound of the function, and the function never reaches it. What about a straight line? Meaning, assume that the original function is pi over 2. What would you say about the asymptote of such a function? Does this straight line have an asymptote, horizontal line more than it's straight, the horizontal line? So in high school, no one would ever ask you that because it doesn't make sense to ask you to do hakira, to investigate a function which is a straight line, because the answer will be in 2 seconds. But mathematicians, when they define things, it's supposed to be a universal definition. And this is an asymptote. This is like the maximum. The function reaches the bound immediately, right? Because it's fixed. And that is obviously will be a limit as well, will be an asymptote as well. But also, obviously, these are the less interesting example. Most of the time, we will tend to the limit and not stay fixed on it. These are most cases, but they include the simplest cases where there is a maximum to the function. In this case, it's both the maximum and the minimum, and it is the limit. Okay, agree? So I'm deleting it because I didn't write anything. I just talked about it. Now we will introduce the much feared epsilon. Epsilon, okay, which is basically just another variable name. It's not a specific number. There is no number epsilon. Epsilon is like X and Y, but it's used in hard to understand definitions, so it's feared. But other than that, just a number. And we will introduce it slowly. Given definition. Given a real number x0 and given a positive value epsilon, we define the epsilon area of xfs, x0, sorry, to be the segment between x0 minus epsilon to x0 plus epsilon. Notice that epsilon is basically a radius of this the radius of this segment where x0 is its center. I'll give a quick example. Choose any x0 as you would like. Choose, that's a call for action. 4, okay. Choose any radius that you like. 2, okay. So we go to the real axis at the point 4, and now we move at most 2 steps to the right, or at most 2 steps to the left. Which segment we will get? The epsilon area of x0 is, from where to where do we get? If we move 2 steps from 2 and 6 exactly. Do you agree? I will show you it on drawing. So if the main point, the center point is 4, 0, and I move 2 steps to the left, I get to 2, 0. 2 steps to the right from 4, I get to 6, 0. Okay, so if let's change its color, the center is the red dot, the area is between the left blue dot and the right blue dot. Agreed? I'm doing it slowly because it's quite important to understand this for the future. Would you say that is a large area or a small area?
Because the area is the same as the number. I mean,
Yeah.
what's the definition of large? It can be very
Exactly. We cannot determine. That's the answer I was going for. There are no large areas or small areas. There are just areas from all different sizes. I was about to say all different shapes and sizes, but that's just progressive propaganda. No, but segments are not from all shapes and sizes. Segments are from of the same shape, and what differs one from another are just the size, but we do go over all sizes. So epsilon will always be the radius of an area, and we'll always say for all epsilon, for all radiuses, for all distances. That's the idea of epsilon. Large as small, all distances. Okay? And now look at the following example. Say, I will first draw and then write mathematics. So say this is A, and this is the supremum of A. Take any epsilon, positive epsilon. Where is M minus epsilon in the drawing? So it's either between the, brackets of A or to the left of A. I will draw it here. But for sure, M minus epsilon will be lower than M, to the left of M. Agreed? Could M minus epsilon be an upper bound of A?
Yeah.
If M is the supremum,
No.
No.
then it's the lowest upper bound, so any lower number is not an upper bound. What does it mean that some number is not an upper bound? To be an upper bound is to be larger than everyone. Then to not be an upper bound,
It should not
Will
be
be
larger than everyone.
I'm not larger than everyone. What does it mean?
In A
No,
or
uh,
less.
and not larger, it's, I mean, it can be or not be.
If
a little bit
I'm not
different.
bigger than everyone, what does it mean?
Are
Smaller than the maximum.
Not the max. There doesn't have to be a maximum.
That's a free-
There's
Smaller
someone,
Bigger
there's
than me.
some element bigger than me. And if there was a maximum, we wouldn't need all this discussion. That's the simplest case. We need to speak about the case, to include the cases where there is no maximum. So there will be some element here. Agreed? So now, I'll leave that as an example, just a drawing, but now I will write a mathematical claim and that this drawing represents. Claim. Proposition, I don't know. Proposition. And given a set A, a subset of the real numbers, and M any specific number, then M is the supremum of the set A if and only if the following the two following conditions hold. Two following conditions hold. First, M is an upper bound of A. And the second, now you need to listen closely. For all positive epsilon, there exists A in A such that A is larger than M minus epsilon. Can you see how the mathematical proposition fits the drawing we had above, right? I'm saying it's an upper bound if it's the supremum, if it is an upper bound, and if I take it a bit to the left, it's not an upper bound anymore. Someone is bigger than that. Okay, we will prove it in a few seconds, but that is the claim. So before I will prove it, just question will be, why should we take something that was clear so far and use that horrible language to present it? And there is an answer, because the definitions above were like storytelling. It's the lowest of the upper bounds. It's great when you already know the answer. Here you have inequalities, algebraic formulas which you can calculate. Usually we use that in order to prove things that will be quite hard to prove without the algebraic notions. So that's the main idea here, and it will happen quite a few times. but this algebraic notation helps us eventually to prove theorems. If we'll try to stay within the the still mathematical, but verbal notions, very quickly we will find ourselves with very convoluted sentences that we don't follow. But when we go to the algebraic notion, it will be easier. But it will be hard at first to get, and when I said first in the first semester, it will be hard to get used to the algebraic notation. So it's important, it's useful, and we're going to do this process together. But it's not just in order to make you suffer. Yes, Thomas.
So to go back a bit, M is a supremum, but not necessarily part of the set.
In general, yes, the supremum doesn't have to be a part of the set. And that's the more interesting example, usually. If M is the maximum, then all proofs are quite easy.
So this means that epsilon, whichever epsilon bigger than 0, makes it so that there is an element bigger than M minus epsilon.
Yeah, which basically this part, I will prove in a minute and go over everything, but this part basically says M minus epsilon is not an upper bound. And it makes sense because M is the lowest upper bound. So everything lower than that is not an upper bound. That's what it says. And again, this is an inequality we can work with and solve for epsilon and be able to calculate things. You will see it in the future. It's just different notation for the very same definition. Yes.
Which cases where epsilon is bigger than 0 would there not exist an A where A is bigger than M minus epsilon?
No, I'm saying for all epsilon it will happen. What do you mean?
No,
If M wasn't the upper, if M wasn't the most strict upper bound, imagine M being here, right? So if you take a small epsilon, M minus epsilon will be here, and no A would pass it. I think you can't imagine it because you imagine M at the right edge of the set.
Sorry, I'm getting mixed up with the biconditionality. Never mind.
Okay. So let's prove this example. It's an if and only if, so I have to prove both direction of if then. Proof. First, assume, that's the easy part, assume that M is the supremum of A. We will prove it is bad. Sorry. So first we assume that M is the supremum of the set, and we will prove conditions 1 and 2. Condition 1 is obvious by definition. I'm saying that I'm given that M is the supremum of the set, then obviously it is an upper bound because the supremum is the lowest, because the supremum is the lowest upper bound of A. Next, I need to prove that for all positive epsilon, for all distances, there exists such an A. I told you it before verbally. Now I will write it. For the second condition, let there be light. Let there be epsilon bigger than 0. In Hebrew, we all say Yehi epsilon gadol me'efes. We assume that we are given an arbitrary value, positive value. To be honest, the letter B, the Yehi, is kind of like a definition of a function in programming. Because when you create a function and are given variables, you assume that someone gave you such a variable, but you cannot know what variable did the user give you. So it's kind of like that. You are given any epsilon and you need to be able to prove that the claim works, is true for this epsilon. So we need to prove that there exists such an A. And why is it true? If A is positive, then obviously M minus epsilon is smaller than M. Do you agree about this claim?
Yeah.
Since M is the lowest upper bound of A, then M minus epsilon, which is a smaller number, is not an upper bound of A.
And
Agreed?
this is only over the set of the real numbers?
All of calculus is over a set of real
Yeah, I
numbers.
mean, that,
Yes, it's
no,
not
I mean, because like,
general. What?
no, because like, this doesn't really make sense for any arbitrary set that isn't the real numbers, right?
Yes, because what is minus epsilon? Yes.
Yeah,
It's not for every partial. It's not a theorem in every partial order.
Discrete math.
Yeah, it's
Yeah.
not discrete math. Stop it. Okay.
Stop it.
Yeah. We're not doing calculus over any discrete calculus. Okay. No, it's over the real number. The only question will be for, I don't know, like half an hour or so, what would happen if we go over the rational numbers and not the real numbers, and what problems will arise there. And we'll have the discussion, and that's it. Other than that, only real numbers. Like everyone smiled, I think they waited for me to tell you to stop it. But yeah, okay. It's okay. I can be a smartest in my class. Okay, since M is the lowest upper bound of A, then M minus epsilon, which is a smaller number, is not an upper bound. What does it mean not to be an upper bound? It means I'm not larger than everyone. That means someone is larger than me. Therefore, there exists A in A such that A is larger than M minus epsilon, which is exactly what we wanted. And a bit more about discrete mathematics here. Remember, whoever took discrete mathematics, what is the negative, not negative, what is the negation of, for all A in A is smaller than M minus epsilon?
Exists A.
Yeah, exactly. There exists an A in A such that A is larger than M minus epsilon. In discrete mathematics, you learn these logics facts. You don't have, whoever understood what I said without it is better off, right? But still, I remind you that it has something to do with logic and discrete mathematics. Okay, so what did we do? We proved that if M is the supremum, then the two conditions hold. But I'm claiming more than that. It's an equivalent. The two conditions are equivalent to M being a supermum. So now we wish to prove the other direction, which we often use. The other direction is usually the more useful. So now on to the second direction of proof. Assume the two conditions hold and prove that M is the supremum of A. How do we prove that a certain number is a supremum of A? I need to prove two things. One,
M is
one is actually the same one. That's why I'm not writing one. But first, we need to prove that M is an upper bound of A. And that is literally condition 1. Right? In order to be the supremum, you have to do two things. One, be an upper bound. Second, be the lowest of the upper bounds, right? So one exactly give me that it's an upper bound. The second condition is equivalent for it to be the lowest, and that's what we'll see. Okay, agreed? Now, given K an upper bound of A, we need to prove that M is lesser or equal to K, right? The lowest of the upper bounds. Given an arbitrary upper bound, the lowest must be lower of the two. ABC, assume by contradiction that K, M, excuse me, is larger than K. Let's draw it for a second. That will be helpful. So this is this is M, and there is an upper bound here of the set A. It's kind of contradictory to the story, but we assume by contradiction, so obviously a contradiction will occur. But how can you describe, that's the hint, how can you describe K using only M? What else can I call K? Instead of calling it just K, that's an arbitrary name, what can I say K equals to?
M minus epsilon.
Some epsilon, but what epsilon would it be?
I mean, the difference between M and K.
Exactly. This will be the epsilon, and there will be an A here larger than K, and I will get a contradiction. That's exactly what I'm going to do. So look at how will we do it. If M is larger than K, then K is actually M minus K. Do you agree? Seems a bit silly, but I hope that the drawing helps you to understand it, right? I'm trying to describe K in accordance to condition 2, right? The A larger than M minus epsilon. But I am able to do it. M is obviously M minus K. Agreed? And M minus K is a positive epsilon. This is a positive number because we assumed by contradiction that M is larger than K. So that is some epsilon, which is positive. By condition 2, if I'm taking M minus epsilon, there exists some A in A such that A is larger than K, which is equal to M minus epsilon, in contradiction to the fact that K is an upper bound of A. I found an element in A which is strictly larger than the upper bound. That's obviously a contradiction. Okay, so we've proven that theorem. You've seen that calculus becomes a bit more complicated, and to encourage you a bit, it is true that all proofs in calculus will be like this. Then that's not the encouragement you are looking for, but not all of calculus are just proofs. The course is built from a certain amount of proofs and a certain amount of calculation. You obviously need to learn both, but you don't have to excel, let's just say, at both. And I think that's different than discrete mathematics, which was mainly built from proofs. Calculus is built from some proofs and some calculation. But my advice to you is not to say, okay, the proofs are hard, I'll ignore them. No, try to understand them. When you try to understand them, they will become clearer and clearer. Whoever tried to understand the proofs, at some point will go back to this one and say, oh, that's so easy. I don't understand what I didn't understand. But whoever will just give up and say, I don't understand the proof, by the end of the course, will don't understand that as well. But the more important thing, he will not understand a lot of what will be going on here. So my advice is to try to understand the proofs and don't feel too bad if they are not completely easy for you right now. It will become easier in the future. So that's enough for today. Have a nice day.
The contradiction, the fact, the assumption makes.
Yeah, the K is an upper bound. K was given as an upper bound, and we found an element which is bigger than it, which is a contradictory.
Can you scroll up?
You can see the person with the most.
Yeah. Wait,
I'm scrolling. Yeah.
wait.
Tell me when.
That was a bit I missed. Wait, keep on going up.
A question you didn't say like how will our course will be scored?
A little bit
Yeah.
more.
It mostly the exam probably be a quiz or something.
Okay.
I'll make sure and get back.
Okay.
Yeah.
Can you go up to where you did the number line on GeoGebra?
I don't know if you're.
No, further.
This?
Yeah, I missed out. No.
Oh.
Yeah, почти.
Right.